When most people hear the word multiverse, they think of movies, comics, or imaginative stories. In popular culture, it has become a symbol of anything bizarre or impossible. But in real science, the idea is very different. It is not magic, not fantasy, and not a storytelling device. It is a set of serious hypotheses that come directly from modern physics. Across several independent fields, cosmology, quantum mechanics, and string theory, scientists repeatedly encounter mathematical results that suggest the same possibility. Our universe may not be the only one. This is not because anyone wants a multiverse to exist. It is because the equations naturally lead to it when we push physics to its limits. Cosmic inflation predicts separate bubble universes that grow faster than light and can never reconnect. Quantum theory suggests that every outcome of a physical process must be realized, but in different branches of reality. String theory produces a nearly infinite number of possible universes, each with its own physical constants. These ideas differ, but they converge on one profound question. If our universe is just one version among many, what might the others look like, and can we ever detect them? This video will break down the real scientific models of the multiverse, explain where they come from, and explore what evidence, if any, could ever confirm them. No fiction, no mythology, only physics. The concept of the multiverse did not emerge because scientists wanted exotic ideas or dramatic theories. It appeared because modern physics repeatedly confronted a deeper problem. Our universe looks unusually well arranged. From the very beginning, the laws of nature seem calibrated with extraordinary precision. The strength of gravity, the charge of the electron, the mass of the proton, the behavior of dark energy, all of these values appear just right for stars to form, for galaxies to exist, and for life to be possible. If any of these constants were slightly different, the universe could collapse immediately, expand too fast for matter to gather, or fail to form atoms at all. This extreme sensitivity is known as the fine-tuning problem, and it raises a difficult question. Why does our universe have exactly the conditions required for complexity? One explanation is simply coincidence, an incredibly lucky roll of cosmic dice. Another is design, but science cannot rely on untestable assumptions. The third possibility is the one many physicists find most natural. Our universe is not unique. If there are countless universes with different physical constants, then it is not surprising that at least one of them has parameters that allow structure and life. We live in that one simply because we cannot exist in the others. This idea gains further support from cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. According to modern models, inflation does not end everywhere at the same time. Instead, it produces vast, disconnected regions, pockets or bubbles, each cooling into its own universe with its own properties. Once separated, these regions can never interact again, effectively creating independent universes within a larger inflating space. Quantum mechanics introduces another reason to consider multiple realities. Its fundamental rule states that every possible outcome of a quantum event must be realized, not in this universe, but across different branches of reality. If the equations are taken literally, then quantum theory naturally creates a constantly branching multiverse. Finally, string theory adds its own support. When scientists explore the mathematical structure of strings and extra dimensions, they find not a single unique solution, but an enormous landscape, possibly 10 to the power of 500 possible universes, each with different physics. In such a landscape, the existence of many universes is not unusual, it is expected. Together, these fields point toward the same surprising conclusion. The multiverse is not an escape into fantasy. It is a serious attempt to answer why our universe looks the way it does, and why its laws appear so precisely tuned for existence. The most scientifically grounded version of the multiverse begins with one of the most successful ideas in modern cosmology, cosmic inflation. Inflation describes a moment in the earliest fraction of a second after the Big Bang, when space itself expanded at an extraordinary, exponential rate. In this brief instant, distances between points grew faster than the speed of light, smoothing the universe, erasing irregularities, and explaining why the cosmos looks so uniform on the largest scales. This rapid expansion is not speculation. Its predictions match what we observe today: the precise temperature patterns of the cosmic microwave background, the distribution of galaxies, and the flat geometry of space. inflation works. But inflation also leads to a surprising consequence. According to most models, inflation does not stop everywhere at once. Instead, it is like boiling water. Bubbles of normal space form within an ever-expanding background. In some regions, inflation ends and gives birth to a universe like ours. In other regions, the expansion continues, stretching space faster than these newborn universes can grow. This process creates an endlessly branching structure called eternal inflation, a cosmos where new bubble universes are constantly forming while the larger inflating space keeps growing forever. Each bubble is effectively its own universe, completely sealed off from the others by the ongoing inflation around it. Once two bubbles separate, they recede from each other faster than any signal can travel, making communication or interaction physically impossible. From the inside, every bubble looks like a complete universe with its own Big Bang, stars, galaxies, and physical laws. And here is the remarkable part. The conditions inside each bubble can be different. Tiny variations in the quantum fields that drive inflation can result in distinct values of physical constants, the strength of gravity, the behavior of dark energy, even the number of spatial dimensions in extreme models. This means that eternal inflation naturally produces a multiverse where each region may follow its own version of physics. Some bubbles may collapse instantly. Others may expand into universes nothing like ours. A few, perhaps very few, will have conditions suitable for complex structures, chemistry, or life. We live inside one such bubble. To us, it appears as the entire cosmos because we cannot see beyond its horizon. Everything outside our bubble is forever unreachable, hidden behind an expanding boundary that no light can cross. What makes the inflationary multiverse especially compelling is that it is not an exotic addition to the theory. It emerges directly from the mathematics of inflation. Once you accept the standard model of inflation, eternal inflation follows almost automatically. Many cosmologists consider it the strongest and most physically motivated version of the multiverse, because it arises naturally from equations already supported by observations. In this view, the multiverse is not an abstract philosophical idea. It is the most straightforward interpretation of how space behaves when forced into exponential expansion, breaking into islands of reality, each with its own beginning, its own evolution, and possibly its own laws of nature. The second major scientific pathway to the multiverse comes not from cosmology, but from the strange and counterintuitive world of quantum mechanics. At the heart of quantum theory lies the idea of superposition, the principle that a system can exist in multiple states at the same time. An electron can be in two positions simultaneously, a photon can travel along two paths at once, and atoms can oscillate in overlapping vibrational modes. This is not metaphor, it is experimentally verified physics. Yet we face a conceptual problem. When we observe a quantum system, we never see superpositions. We see a single definite outcome. A particle is here or there, but never both. Traditional quantum mechanics solves this by invoking something called collapse. The wave function, which describes all possible states, suddenly and mysteriously reduces to one state when observed. But collapse is not part of the underlying equations of quantum physics. It is simply added as a rule that raises deep questions about what measurement really means and why the universe should behave differently when someone looks at it. In the 1950s, physicist Hugh Everett proposed a radical alternative. What if the wave function never collapses at all? What if every possible outcome of a quantum event actually occurs, but in different branches of reality? In Everett's interpretation, often called the many worlds interpretation, the universe does not choose a single result. Instead, it splits. When a particle has two possible states, the universe branches into two versions, one where the particle is in the first state, and another where it is in the second. Every quantum interaction, every atom, every photon, every fluctuation, causes this branching to continue, creating an ongoing structure of parallel realities. This is the quantum multiverse. It is not a collection of bubbles in physical space, like in inflationary cosmology. Instead, it is a vast mathematical structure embedded in the wave function of the universe itself. Different branches do not occupy different locations. They occupy different histories, distinct, non-interacting outcomes of every quantum event that has ever occurred. In this view, when you measure a quantum system, you do not force it to choose one outcome. You simply become part of the branching process. There is a version of you who observes one result, and a version who observes the other. Both are equally real, but unable to communicate, because their worlds evolve independently from that moment onward. Although this interpretation is philosophically striking, it is built entirely on the standard equations of quantum mechanics. Everett removed the additional rule of collapse and kept only what the mathematics already predicted. That makes the many worlds interpretation deeply attractive to many physicists. It is conceptually simple, mathematically rigorous, and free of hidden variables. Its weakness is not lack of theory, it is lack of direct experimental access. Parallel branches cannot interact, so we cannot observe them, even if they exist. Still, the quantum multiverse remains one of the most serious and widely discussed possibilities in modern theoretical physics. It suggests that the true structure of reality is not a single line, but a constantly branching tree, a dynamic, ever-expanding web of all possible outcomes. The third major path to the multiverse comes from string theory, one of the most ambitious attempts to unify all fundamental forces of nature. In string theory, the particles we observe, electrons, quarks, photons, neutrinos, are not point-like objects. They are tiny vibrating strings. Each mode of vibration corresponds to a different particle, much like different musical notes on the same instrument. But these strings do not vibrate in the simple three-dimensional space we see around us. To be mathematically consistent, string theory requires 10 or 11 dimensions. 7 or 8 of these dimensions are hidden, curled up, compactified into shapes so small that our instruments cannot detect them. And here lies the central idea. The specific way these extra dimensions fold determines the laws of physics in that universe. Different geometric shapes lead to different vibrational patterns of strings. Different patterns produce different particles. Different particles form different versions of physics. This means that string theory does not predict a single set of physical laws. Instead, it produces a vast number of mathematically allowed configurations, an enormous collection known as the string landscape. And that landscape is huge. Estimates vary, but many calculations suggest numbers like 10 to the power of 1 to 10 possible universes, each with its own constants, its own particle spectrum, and its own vacuum energy. In some of these universes, gravity might be stronger. In others, atoms might not be stable. In many, stars could never ignite or galaxies could never form. But all of them follow the rules of string theory. Our universe is simply one point on this gigantic landscape, one valley in the complex terrain of possible solutions. Nothing in the mathematics favors our particular valley. It is just one of many. From the perspective of the theory, it would be surprising if only one set of physical laws existed. The landscape suggests that many possible universes are equally real within the framework of string theory. What connects this to the broader idea of the multiverse is that cosmic inflation could populate different regions of this landscape. Each bubble universe born from inflation might settle into a different vacuum state of string theory, giving rise to its own physics. In that picture, the inflationary multiverse and the string landscape work together. Inflation creates the universes, and string theory determines their properties. Although direct evidence for this idea is still beyond our reach, the mathematical foundation is solid, and the landscape appears naturally within the equations. The string multiverse is not a philosophical invention. It is a physical consequence of trying to build a single theory that unifies all forces and particles. In this view, the question why does our universe have the laws it has may have a simple answer. Because it is just one possibility among an almost unimaginable number of mathematically valid worlds. In the framework of eternal inflation, space does not expand uniformly. Instead, new bubble universes form continuously within an ever-inflating background. Each bubble undergoes its own Big Bang-like event, develops its own physics, and becomes an isolated cosmic region. Normally, these bubbles expand into the surrounding inflating space, drifting apart so rapidly that they never encounter each other. But in some inflationary models, bubble universes can form close enough that, before they separate beyond causal reach, they collide. A collision between universes would not look like galaxies smashing together. It would happen at the boundaries of two expanding regions of space-time itself. The interaction would imprint disturbances on the earliest moments of each universe's evolution, particularly during the formation of the cosmic microwave background, CMB. Because the CMB is the oldest light we can observe, any event that happened in the first tiny fractions of a second could leave subtle fingerprints on it. Theoretical work predicts several types of observational signatures. One possibility is circular anomalies, large, faint rings in the temperature map of the CMB, caused by shock-front symmetry when two bubble walls meet. Another is localized temperature shifts, where one region of the sky appears slightly warmer or colder than statistical expectations. A third clue could be unusual polarization patterns, reflecting distortions in the primordial plasma caused by a directional disturbance from a collision event. Scientists have searched for these patterns using data from WMAP and Planck satellites. A few areas of interest have been identified, such as the well-known CMB cold spot, but none of these features meet the strict thresholds required to claim evidence of another universe. They may be statistical noise, cosmic variance, or unresolved astrophysical structures. Even without direct confirmation, bubble collisions remain a natural prediction of many inflationary models. If eternal inflation is correct, then our universe is just one bubble among countless others, and collisions may have occurred in the distant past. Whether they left detectable max is still unknown, but the possibility motivates some of the most sensitive cosmological observations we perform today. In this sense, the idea of bubble collisions is not speculation added on top of the theory. It is a consequence of the same physics that successfully explains the large-scale shape of our universe. The search continues not because we expect drama, but because subtle clues in the sky might one day reveal that our cosmos once brushed against another. At the present moment, we do not have direct evidence for the existence of other universes. No telescope can see beyond our cosmic horizon, and no experiment can probe regions of space-time forever separated from our own. If the multiverse exists, most of it may be permanently inaccessible to observation. But the absence of direct proof does not mean the idea is unscientific. In modern cosmology, the multiverse appears not as a fantasy, but as a potential solution to several profound and persistent problems in physics. First, there are the subtle irregularities in the cosmic microwave background. The CMB is the oldest light in the universe, an almost perfectly uniform glow left over from the Big Bang. Yet it contains tiny fluctuations, slightly warmer and cooler spots scattered across the sky. These fluctuations match the predictions of inflation, but some of them are unusual enough that scientists have explored whether they could be hints of interactions with regions outside our observable universe. Features like the cold spot, hemispherical asymmetry, and certain large-scale alignments have been studied repeatedly. None of them rise to the level of definitive evidence, but their persistence keeps the question open. Are these anomalies artifacts of cosmic variance, or do they point to physics beyond our horizon? Second, there is the fine-tuning problem. Our universe appears precisely calibrated in ways that seem almost improbable. The strength of gravity, the mass of the electron, the density of dark energy, each of these constants must lie within a narrow range for stars, galaxies, and chemistry to exist. If cosmic inflation or string theory naturally produces many universes with different constants, then fine-tuning becomes a statistical outcome rather than a mystery. We live in a universe compatible with life because life can only emerge in such a universe. This is not a metaphysical argument. It is a direct application of probability to a large ensemble of possibilities. Third, the multiverse helps address a fundamental challenge in theoretical physics. We have no simple, unique model that explains why our universe has the laws it does. Modern theories like string theory do not produce one inevitable set of physical laws. They produce a landscape of solutions. Inflation does not produce one uniform cosmos. It produces many distinct regions. Quantum theory does not select one history. It allows all of them. When independent areas of physics all point toward multiplicity rather than uniqueness, it becomes plausible that our universe is just one realization among many. For these reasons, the multiverse is not dismissed by serious scientists as speculative fiction. It is considered because it arises naturally from equations that already describe the universe with extraordinary accuracy. Whether we examine the origin of cosmic structure, the behavior of quantum systems, or the fundamental constants of nature, the same idea keeps appearing. Our universe may not be the only one. We do not yet know whether this picture is correct. But the multiverse is a legitimate scientific framework because it attempts to answer real problems that no single universe model has fully resolved. If future observations reveal subtle signatures of bubble collisions or confirm certain inflationary predictions, we may gain indirect evidence that our cosmos is part of a larger structure. Until then, the multiverse remains a compelling interpretation, one born not from imagination, but from the mathematics of modern physics. The multiverse is a serious scientific idea, but it faces equally serious challenges. The first issue is the principle of falsifiability, the core of the scientific method. A theory must make predictions that can, at least in principle, be proven wrong. But if other universes lie beyond our cosmic horizon, forever unreachable by light or matter, how do we test their existence? Critics argue that a theory describing realities we can never observe risks slipping out of science and into philosophy. Supporters respond that indirect evidence, such as patterns produced by inflation, could one day offer testable predictions. Still, the question remains open. Can a theory about what lies outside our universe be scientifically verified? A second difficulty concerns the string landscape. String theory naturally produces an enormous number of possible universes, perhaps 10 to the power of 1 or more, with different physical laws. But this abundance creates a problem. If the theory allows almost anything, how do we determine which version corresponds to our universe? A model that explains everything can also fail to explain anything. Without a method to select one vacuum state over another, critics argue that the landscape lacks predictive power. The challenge is not that string theory is wrong, but that it may be too flexible to guide observations. The third issue involves the Everett, or many worlds, interpretation of quantum mechanics. It offers an elegant solution to the measurement problem by removing wave function collapse entirely, but it also implies that every quantum event creates new, non-interacting branches of reality. The difficulty is that these branches cannot be accessed, influenced, or detected. If no experiment can reveal the presence of these parallel histories, then, some argue, the many worlds interpretation may describe a mathematical structure rather than a physical one. Its beauty does not guarantee its testability. There is also a broader philosophical criticism. The multiverse sometimes explains too much. If any observed property of our universe can be attributed to we live in the bubble where this happened, then the theory risks losing predictive force. A good physical theory should narrow the range of possibilities, not expand them without limit. The multiverse, depending on how it is framed, can be accused of doing the opposite. Finally, many scientists worry that the multiverse may be mathematically compelling but permanently unreachable. A theory can be internally consistent, elegant, and rooted in modern physics, and yet remain impossible to test experimentally. The multiverse sits at this boundary. It may one day become testable through signatures of inflation or through fundamental theoretical breakthroughs, or it may remain forever outside our observational reach, describing realities that exist in equations but not in our instruments. For now, the multiverse stands as both a powerful framework and a profound challenge, a theory that attempts to solve the deepest mysteries of nature, while confronting the limits of what science can ever prove. In the end, the question of the multiverse is not a leap into imagination, but a consequence of the physics we already trust. Inflation, quantum mechanics, and string theory, three pillars of modern science, each point, in their own way, toward a reality far larger than the one we see. None of these theories were created to support the idea of multiple universes, yet all of them seem to lead us there. This does not mean the multiverse is proven. It means that the structure of our universe is stranger and more complex than the boundaries of our observations suggest. For now, we stand in a single cosmic bubble, unable to see beyond its horizon, unsure whether our world is unique or simply one example in an enormous cosmic landscape. But as our instruments sharpen and our theories evolve, physics grows closer to a picture in which our universe is one cell in a vast cosmic foam, one region among many, each governed by its own laws of space, matter, and time. Whether or not we ever confirm the existence of these other worlds, the idea changes how we see ourselves. It reminds us that our reality may not be the central chapter of existence, but one story among countless others written into the fabric of space-time. And so the video closes with a thought that blends science with wonder. If universes grow, vanish, and intertwine, then our story is only a single line in an infinite cosmic library.